we are looking for fully differential op amps or fully differential systems. The typical differential op amp can be connected in this fashion. You can see from here, these are two inputs of a differential op amp, and you are receiving V in 1 and V in 2, and there are two outputs VO1 and VO2 which are fed back in a negative fashion, negative feedback from both sides, and if you have only single ended, the output could have been in the center, okay, which is what we have already done earlier. In this case we have two outputs and we are feeding it back. Please remember both are negative feedbacks. Right now, for the sake of this stability and everything and performance, I chose R1, R1, R2, R2, but they are different. Also can be solved a case in which there are some issues will come later. Now why differential, we already discussed it last time. One of the interesting point we said there was anything noise sitting on these can be cancelled, okay, because if you take the difference of VO1, VO2, the noise which is superseding either inputs can also get cancelled by subtractions. This is what we said, but there are a few more interesting things which is of relevance, and I think that should go first before we start noise. For single output op amp, a typical amplifier shown here, which is an inverting mode amplifier, and the output looks something like sinusoid. Let us say if input is a sinusoid and you receive VO max, VO min, if there is no distortion then VO max will be equal to VO min, and we define a output common value VO common or VCM as the common mode voltage at the output, which is sum of VO max plus VO min by 2, okay. The maximum you can reach is VDD, the lowest you can get to VSS, and therefore sum could be 0, or if VSS is 0 it could be anything else. So VCM is something which you can decide how much you want by deciding up to which these two will actually go. In case they are equal as the shown here, then the VCM is VOC is, or maybe VOCM I should say, or VCM we shall say latter, is 0. Please look at it, the system which I have shown you earlier just a minute before, this is symmetric to this, okay. This is symmetric structure, is called balanced structure. In case of balanced fully differential system, we can also figure out what will be VO1 and VO2 independently, okay, and if I subtract, what can happen at the net output which I am going to get. So I repeat, this is a single stage op amp or a single ended op amp, and now I am using it similar structure which I shown earlier to have a differential mode op amp, fully differential. So you may have for VO1 and VO2, because of opposite polarity they may look like this, and if I subtract, take a differential of them, the peak values is VO max minus min minus VO max minus VO min, and if they are equal and opposite, then twice of the earlier values you can attain. However, the common mode, which is still subtraction of the two, is still 0 because we are holding them equal. This and this and this are same, so the common mode is still average value, which is still 0. So please remember that by making a differential I am still able to get VCM 0, which I wish, if I can set any other value, but we can get the output which is VO1 minus VO2 differential output is double that of the single ended ones. So one feature of the fully differential is you can get twice the value of outputs, swings. So what is this called? The swings. The swings in the case of differential op amps is larger compared to single ended system. Many applications require larger signal outputs, but you do not want to reach saturation, this nonlinear zones in VO-VI. This may be one possibility in which you can get larger output swings. Is that point clear? Otherwise, for larger output, if input increases, you may reach into a non-linearity zone of VO-VI characteristics, and then you get distortions. We will see that later. Now the problem which is why this kind of amplifiers are used, one is of course swing, the other is of course for most of the circuit which requires higher gains, differential systems are very popular. But as soon as I say higher gains, we will see what kind of loads I should have compared to single ended op amp, which we already discussed. So the issue, let us say we need an amplifier which has a higher gain, and we also desire that such an amplifier has large signal to noise ratio. For your sake of those who have not done earlier this, a signal to noise ratio is the maximum signal output power divided by output noise power, okay, is the ratio of this is called signal to noise ratio, SNR. If V square signal is the peak value of which, this is the peak value of this square by 2 is the maximum signal, and output noise power is gone VON bar square or VON square bar average value. Please remember, if I use I will solve this in the noise case these values, but these are trivial. One can solve that VON square for a single ended case is 1 plus R2 by R1 square 4 kT R1 into Fn, and Fn is called the noise bandwidths. This 4 kTr is something probably we will see soon in few minutes, which is essentially the thermal noise of a resistor. So the output noise voltage square, of course, always expressed in square terms. The Y square, anyone? Essentially represents power. So V square by R, if R is 1, we represent power by V squares. Whereas in the case of fully differential, it happens to be twice that of this square. However, you also see the swing in the case of single ended is just VO max minus VO min, where in the case of full differential it is twice that of VO max minus VO min. Swing is also larger. So if I square this, I will get 4, this is half, so still SNR will be how much, larger or smaller? Twice that of single ended op amps. Is that clear? This will give you 4, this is half, so 4 by 2, which means at least signal to noise ratio will double when I use fully differential systems. There is another term which we will see in the case of analog designs, which is called noise figure. Noise figures is explained as SNR at the output divided by SNR at the input divided by SNR at the output. Some other time when we come to actual noise figure calculations. These are the specification for a given amplifier. They will specify you typically what is the SNR needed. Okay. So the kind of thing which I was trying to talk to you, that for higher gain one, and the second is higher SNR. So if you are fully differential, one can say is twice that of single ended amplifiers, and larger the SNR, better is the amplifier. Is that clear? Signal to noise ratio larger means lower noise, higher signal in a ratio. Okay. So it is better to use differential amplifiers, fully differential amplifiers instead of single ended op amps if you are looking for higher SNRs.
Sir, but in single ended there are AC current is twice at that point.
Where? In single ended the problem is slightly different. In this case single ended, since the one end of the circuit we are only putting diode connected load, so the load at the one end only is RO3 parallel RO4 in the single ended op amps, whereas in this case now I will show you I can have larger ROs on the both sides, and that by increasing the gain as well as increasing the SNRs. Okay. Okay, this the equivalent circuit of a differential amplifier both at the input and output, I will post it on the website, you can check it, it takes a little time. One can express inputs for the differential stage. I will please read it, in case you don't I will come sometime. Then I can get some relationship between VID, IIC, VICs. By similar argument I can put an equivalent T network for the output of a fully differential system, and again I can get VO1, VO2, VOD and VOC accordingly. This is what has been done, and using this we will be able to calculate ACM and ADM for a fully differential amplifiers. Okay, please remember, I am sorry I am not able to spend time on this because there are lot many things to be done, but I am going to post it so you can look all of it. For example, before we go ahead, the VOD is VO1 minus VO2, which is called ADM times VID, and for common mode VOC is VO1 plus VO by 2, which is ACM times VIC. So we can evaluate both VODs and VOCs, and what is important for us in this particular, this common mode voltage should be fixed, and let us see why I am so much worried about fixing the common mode voltage. The theory about this, please read it on my website. In case there is an issue there, maybe some other day I will again explain to you. Just figures do not write right now because it will be available to you. We keep saying to maintain a good common mode voltage, we have said that normally fully differential systems are used for higher gains. Okay. Now if you see, if you are, this is your standard double-ended op-amp, okay, one at VO1 and other is VO2, and to make it common mode, or rather to make it simpler to first to understand, I have connected output of this to the input of this. In normal case what will be here, the resistance output to input R, but right now I chose R to be even feedback can be negative feedback, differential feedback. So this is a differential feedback which I kept, this is your bias circuit. These devices receives a potential VB which decides the ROs of M3 and M4. Is that point clear? M3 and M4 receives a potential VB which decides the RO3 and RO4 of this. This is not diode connected load, this fact has to be appreciated. This is through P channel, and the lower current ISS is governed by this N channel mirror shown here. Now the problem which is worrying me right now is this: if everything goes well, what is the output resistance of this arm? RO3 parallel RO1. What is the output resistance of this arm? RO4 parallel RO2. So GM times that is the voltage which I can get, gains I can get individually. My problem is now something more. My assumption is this current is ISS is governed by this device, and this potential is governed by this P channel device, which is also a current source. Let us say for reasons, variety of reasons, sizes, abilities, whatever reasons, these two currents are not equal. In a Kirchhoff law one forces the current should be equal, but let us say it starts with, to equivalent saying I may say, okay, to put it non-equivalent sake I put a small resistor in between which probably can then control the current and then drops here or not drops here. Now this issue which looks to be very odd is very interesting for to understand. If this current which is essentially flowing in this current in IDS3 or IDS4 is not same as ISS by 2 and ISS by 2, we want them to happen, but let us say for variation purpose it does not occur. Okay. Now what can happen? There are two possibilities can happen. This current is larger than ISS by 2, or this current, either way this or this current is less than ISS by 2 because of the P source current is not same as N source current. Is that clear to you? Now if that happens, let us say what are the problems which we can get. I repeat, this is essentially, please just see the figure. I am saying equivalently saying this is given in Razavi's book, this is I7P, or maybe right now I can say this is I6N, and across them there is output resistance ROP and RO for these sources RON. If these are not equal, in this arm there will be IP minus IN, which is whichever is higher, minus plus sign will appear, and since at this node these are parallel resistors, so there is this at this node I have IP minus IN times ROP parallel RON. Normally what should have been there? Zero drop across, there are two current sources, no drops there, they have balanced it out, but it may happen that P channel current may not be exactly same as N channel current, and because of that this node voltage is not at 0. Is that clear? Now this is a worry which in real life occurs, okay, it is not something which I am thinking about as a new thing. Now if that happens, as I said, the other things are explained normal op-amp business, so there is nothing more to write. What is negative feedback's purpose? To stabilize the system. I am stabilizing, so I believe that with this any change should have actually been managed, but to my surprise I find this negative feedback, which is actually a differential feedback, does not solve the problem which I am going to face. Normally what is the negative feedback purpose? Is to stabilize the system. It should pull down or pull up to get to a normal mode. Here I am now trying to show you it does not, even if there is a differential negative feedback, this does not return to equivalence. Okay, so here is the issue which you should look into. You can write down if you wish. The last line is what is bothering me, that the current in M3 or M4 may be larger than ISS by 2 or less than ISS by 2 if P channel currents are not same as N channel currents. Now if this happens, what can happen to us? Please remember ISS is controlled by whom? 5 M5. IDS3 and IDS4 are current controlled by M3 and M4, is that which are governed from 6 and 7 mirrors, okay, M6, M7 mirrors. You first write down, then we will take the two cases and will happen what is going to a problem if this happens. Please envisage, Raj, what could have happened if say it is larger, IDS3 is larger than ISS by 2. What could happen? You cannot hold this situation, so if you want to make it equal, then what should happen to something? Some transistor must change its status, otherwise two currents cannot be equal. Is that correct? The change of status is worrying me the most, because change of status means the resistance of that device will change, and if resistance changes my gain changes. So though my common mode, I mean differential mode feedback was there, but I still see change in outputs, okay. But let us see, you finish this, then I will discuss this. The two issues of interest is, let us say the current, drain current of M3 or M4 is larger than ISS by 2 or less than ISS by 2. These are not issues which are trivial, this is in real designs, these issues keep coming, at least in fully differential stage. This is what we are elevating, and that is why they become very popular op-amp systems for many of the applications, fully differential. But what is the problem? Cost, extra kuch karo, pay for that, okay. When I already shown you, fully differential can always be used as single ended, look at the single end only and do not worry about the other one, okay. So there is no issue if we really use this as a single ended amplifier. IDS 3-4 is the current, drain current of M3 and M4, is that correct? ISS by 2 is the current in M1 and M2, half of it. Okay, as I said, this has been given from Razavi's book, though my nomenclatures are slightly different from them, and the way I have written they might not have written. So that is the only difference, but the content is same as Razavi's book. This is under the section in op-amp called common mode feedback, okay, CMFB. अभी आ ही रहा है वो, आपको वही दिखाने की कोशिश की जा रही है. Is it okay? So case, take the first case, IDS 3-4 is larger than ISS by 2. Please remember ISS is controlled by 5 transistor current which is coming from N channel mirror, whereas IDS 3-4 is coming from M7 mirrored P channel. Now if these are greater, we will like to restore IDS 3-4 equal to ISS by 2. That is the natural in a Kirchhoff law, in a one arm positive to negative end one current only can flow, but in reality right now it was instantaneously, it did not, which means VO2 or VO1 to be same in normal cases. However, currents in M3, M4 then must reduce. I must say what is there. Let us say this is my current in M1 M2 ISS by 2. This is coming from IDS 3-4 which is following because of the current in the drain current of M6, M3 or M4. If this current has to reach here, what should I do? It should traverse back to reach this point, and what is this point then will make 3 and 4 enter into, because that Vx value if I have to fix a VO1 VO2 I have to same, then M3 M4 must come out of saturation and try to enter linear mode. Is that clear? You said that current is larger, but the current which N channel M1 M2 was received was ISS by 2, this was larger, so it tries to reduce itself so that the currents are same, so that Kirchhoff law is valid, and if that happens M3 M4 comes out of saturation. What is the advantage of the system we were discussing? High gains. Did we now have the high gains? Because M3 M4 would be in a linear zone which is a smaller R-on, therefore gains will actually fall. Is that correct? Gains will actually fall. Now this is an issue if IDS 3-4 is greater than ISS by 2. The possibility exists N channel current may be larger than P channel, so opposite can also occur. Okay. So to say IDS 3-4 is less than ISS by 2. ISS by 2 is coming from which device? M1 and M2 or M5, is that correct? M1 M2 is receiving current from the tail current M5 which is ISS, which is coming from N channel M6 transistor, is that okay? So let us, as everyone thought over it, so let us go to the next case. If IDS 3-4 is less than ISS 4, ISS which is supplied by M5, now we say IDS 3-4 is here and M1 M2 which is receiving half the ISS current from I5 is following this IV law. Okay. Now what will happen? If this is to be made equal, then M5 will now come out of saturation. What will happen to M5 if it comes out of saturation? Then the REE or this RO5 becomes very small. Do you recollect what will happen to some other parameter of op-amp? The common mode gain is proportional to 1 upon REE. If that becomes, common mode gain will increase. So what will decrease? CMRR. So if it does happen that the other current is IDS3 is smaller than this, the amplifier Vx may remain same, VO1, VO2, but device will now show you much lower CMRR. Is that clear? So a case which looked very trivial otherwise has actually, though we have a differential feedback, we are connecting gate to the output. So we have a feedback, and in spite of that such a situation is, or it is not returning back, it is actually reaching one end. Okay. This is something is not correct. So if I can make something common mode constant, then my CMRR will not be dependent on this situation. So let us see further, is that okay? 5 transistor current will reduce so that it becomes equal to IDS34 or IDS3 whatever it is, which means M5 will come out of saturation, and therefore by doing this it will actually reduce the increase the common mode gain or reduce the common mode rejection ratio. Okay. Now these issues are looks to be many people believe this never happens, but it is not so, it does happen, and you need to put a circuit which is called common mode feedback, which retains the common mode. If something increases it will reduce, if something goes down output it will pull it up, okay, so that always CMRR remains constant, so is the gain, the output resistance remain as high as they can be. Okay. So now we say average of op-amp output is defined as common mode output CBCM, which is VO plus VO minus by 2, Let us say by full swing we get VO plus goes to VDD, VO minus goes to VSS, and let us say VDD is 2.5, VSS is minus 2.5, then what is VCM? 0, okay, VCM is 0. But let us take a single supply op amps in which VDD is 5 volt and VSS is 0, in which case VCM is 2.5. I can actually decide to have any of the VCM values between VDD and VSS of my choice, okay, which I can fix. So it is necessary for a fully differential amplifier to be stable, just differential feedback does not help you, and one needs what we call as common mode feedback or CMFB as the word goes, and this allows you to fix a value of VCM. Is that correct? Because VOs are coming out of the current, so if you can fix them, then the outputs will be always, VCM will be always adjusted to VO max plus VO min. Please remember, it need not be VDD, it need not be, it can be any value in between 0 to VDD, okay, minus VSS to VDD. You can fix anywhere, choose any value, average of those two will be the VCM value, which is DC value which you want to decide on. Okay. Now how do I decide? Normally I will prefer, if it is double ended I should keep VCM 0. If it is single supply rail, then I should have to fix VCM value to a fixed choice of my choice. How do I then give a feedback? Here is something, has everyone noted down? These are something not necessarily useful directly in real. SPICE also fails many times in not having, if you do not have CMFB circuit, your amplifier may not function properly, it starts actually ringing too much for a long time, output never settles. Okay, these are some issues which you will see in real life. So you must put CMFB circuit to stabilize that out. Okay. A typical CMFB circuit is shown here. This is your DFAM, and this IDS3, IDS4s are coming from some VB and mirror as we did. I actually do one thing, I figure out what is VO1 and VO2. So I must first sense them. Okay. So there is some circuit which is called common mode sense circuit. It figures out what is the VO1 and VO2 values. Okay. Then from those two values it generates what we call as CMFB voltage, VCM. Then we compare it with the desired value which is chosen VCM, which is called reference voltage in a comparator. If it is larger or smaller, correspondingly the control voltage, call it V control if you wish, will be larger or smaller, minus or plus, or whichever values you fix. This value can control the voltages to either these two or these two. I have shown you both ways. Some people actually control these currents, some people control this current. Anyway, you have to bring it down to equal from either on the top or from the bottom. So please remember, we sense VO1 and VO2 outputs, sense them, generate this, compare with reference, create a control voltage which controls the currents in either IDS3 4 or IDS3 IDS3 or IDS4 or ISS. One of them can be controlled. So either we can change the tail current or we can change the load currents. Why when these circuits are shown? This is the principle behind the CMFB circuit which we are going to show, and in that case the way circuit which I have, I am controlling the load currents. Okay. But same can be used for I5 current also, ISS current. क्या problem हो सकता है if I use CMFB circuit, which is also to some extent an amplifier kind of system? What can it create? It can create stability issue. You are increasing another RC time constants with it. Is that clear to you? एक नया डिवाइस लगाया, उसके साथ एक और RC आया, the system may become unstable. So in a normal case of op amp, how do you stabilize that? By actually putting a Miller capacitance in series to a resistance, pole splitting or directly Miller poles, okay, so that the phase margin is relatively 50 degree around. So you will have to do full analysis with two-ended completely supported by RC network and figure it out whether even with this it stabilizes. Okay, so there is a it's not so trivial, but typically if the loads are larger it happens to be stabilized, so you do not have to do it, but I do not want to say a priori unless you see that. So let us say I put 10 puff, yes it will stabilize, this is natural phenomena, okay, but some other time. Okay, is that okay, Siddhant? So here is the circuit which is very simple and popular. Please remember I am only generating VCM FD, this is only generating the common mode feedback voltage, how to generate it, which includes the comparator, so it is essentially control itself I am generating. I have two transistors M1 and M2 which is my sense, which is receiving signals VO1 and VO2 or VO plus VO minus, is that okay Santosh? M1 and M2 are my sense devices, each receives VO plus VO minus or VO1 VO2 whichever names we have been following. Then there are another two transistors M5 M6 which are so connected that the source of this all are N channels, okay. The source of this is connected to M1 and source of this is connected to source of M2, is that okay? M1 source is connected to M5 and M6 source is connected to M2. M5 and M6 receives the value of VCM which you want to set for, okay, that is the value you set there. Then this M7, M8, M9 are essentially our current sources because they are given from a fixed supply VB1, VB2 maybe from the band gap references, okay, so that these are constants. So please remember these are current sources. You can also ask me, I could have done one single current source, think of it why I do it in series, okay, think of yourself, if not maybe I will ask later. I could have done with one series transistor, one bigger transistor or the L length is larger which I had tried. What is larger length helps? The lambdas are higher and therefore you get lambdas are smaller, therefore you get larger ROs. So this is some kind of pseudo cascodes, okay, it is not really cascode but it is called pseudo cascodes, okay. Okay, these are current sources, same currents are flowing here. Now let us say VO plus and VO minus are such that the average value of them is larger than the common mode voltage, this is the first possibility. These are larger, that average value of them is larger than the VCM. The other case could be they are smaller so that their value, average value is smaller than VCM. So two possibilities. If they are larger, what will happen to currents of these? If VO plus and VO minus are larger, M1 and M2 will draw larger currents, VGS will increase with them. But they are actually getting currents from the current sources. These are of course diode connected loads, okay. These are, I am pushing fixed current, please look at it, I am pushing fixed currents, is that okay? But these two start drawing larger current, so which will draw smaller current? M5 and M6 will draw smaller currents because they are, that is what we are added actually, okay, that together gives me these two currents. So if VO plus and VO minus or VO1, VO2 average value is larger than VCM, these will draw larger currents, but for that these two should draw smaller currents. Now if these two draw smaller currents, then the voltage IR drop across this will be smaller and VM voltage will increase. If I increase the voltage, I can correspondingly change the load resistance currents or I5 currents, is that correct? Now take the next case, if these are smaller, what will happen? They will draw lower currents compared to this, they will start increasing the current, So VCMFB will actually go below. So it will increase or decrease as per requirements of increase or decrease of VO plus and VO minus, and average value will be then retained to VCM. VO plus VO minus, either way it will bring it back to its VCM value. Once the common mode feedback is fixed, settles, that means your common mode rejection ratio is permanently fixed by you. This is something which CMFB allows. Few more things, of course I do not want to say more. These two currents are actually fed to the diffam stage what we have seen with other cascode stage down at the single stage cascodes. So it also divides the current in diffam as well as the single gain stage. I have not shown the circuit. These currents can be chosen such that they feed both to difference as well as the cascode stage or gain stage. Change in those currents will decide if the diffam stage is going down, it will actually boost the cascode stage. If the cascode stage goes down, the diffam stage gain will increase, okay. So that the output gain remains constant with the CMFB, which I have not shown here, but that is why it retains higher gains and constant common mode value, which fixes higher SNRs, higher gains and stability. Of course for stability I repeat, you may have to do a RC network for your both ended op amps. Is that clear? That you cannot avoid, because this network is going to create additional poles and zeros. So the system has to be stabilized. So you must actually do more RC network analysis to get whether your system is still stable. But remember, if the double ended outputs have a larger load to drive, which is one of the major purpose of this, then compared to all others, that they will be the dominant poles and they will actually govern all the bandwidths and no other instability issue will come, okay. But this is something guesswork which I am telling, unless you do, one does not know. So do you get the point why I did common mode feedback? Because this is one of the major circuit which you will use in all your actual designs. Whenever there is a issue of stability or ringing starts, look at it, somewhere your gains, the currents are not matching. This matching problems can easily be handled by one common mode circuit. Price is additional power, lower bandwidths and extra area. So of course all this is at the cost of getting perfectly good highly stable and high SNR amplifiers. Is that clear? This fact has to be understood in actual designs, because these are not normally used by everyone. We can do, and many times your circuit may function without that, but if it does not, the solution. Please remember, every circuit I show does not mean you have to put it. If you design and it works, God saved you, okay, but if God is not ready to save, you can save yourself, okay. That is the trick behind all of it. This finishes everything related to op amps. Of course there are few more things, unending hai, okay. Few more things you must remember. Whenever I want gain stage to higher, must cascode. This is something which we learned day one, cascode it. If I want to improve the bandwidth, see to it that the first dominant pole is at least far away, so that the other poles shift further. So the shifting of poles is one of the best is null. If you null it, your dominant pole is in your hand, okay. So try to use null techniques, but nulls are not very easy to attain, but as much as you can, okay. These are tricks which, and as much as possible, if you know higher SNR, higher gains, use always double ended fully differential system. The biggest advantage they give, the noise is eliminated, even what is else is eliminated, the offsets are also eliminated. What is an offset voltage? The output is 0 but input differential is still there. So which means you have to offset input to get output 0. This value also automatically gets cancelled because differential, this output also equally equal, so both cancels in differentials, okay. So these are very ideal amplifiers, okay. Okay, so this finishes essentially the op amp based systems. Please read Rosardi, Boyce, Baker, Gray, whatever books you have. मैं सिर्फ बता ही सकते हैं, आपको करना पड़ेगा. So we start now another area of interest which is actually not necessarily to analog, but in analog it becomes very worrisome problem. Though the word which all of you are so familiar, noise. Why I brought it before other few things left, because I thought that this is an issue which is also needs to be taken care during the design itself. Okay, just now I talked about SNRs, so this that preceded this, but actually it should follow after this. Okay. So we will look into noise with following points. First, what is a noise, and what types of noise, and then the MOS model for the noise, because we are interested not on all other devices, we are more interested in MOS circuits, so we will look more MOS models. And finally, for given MOS circuits, how do I evaluate the noise? Okay. The word which we use in the case of amplifier is noise at which level we connect it. Input reflect noise is what we are interested, and not at the output. Noise not at the output, but because of the output what input noise you will receive is of relevance, and we will see why I look into that little later. What is a noise? Noise is anything which is unwanted or undesired signal which couples with desired signal, or this is termed noise. So noise is not something very odd or bad or something. None of you are from anyone from communication background here, all micros. Okay. In communication you will learn later that noise is not all that bad. Okay. There are algorithms which use noise to improve the signal to noise ratio. Okay. You actually AGN noise you add, and you actually get a better figures, better images, at least in image processing. So do not go by my statement that noise is bad. Okay. Noise is generated due to a random process. Okay. And limits the minimum signal level that a circuit can process with reasonable but acceptable quality. Noise is generated due to random process and limits the minimum signal level that a circuit can process with reasonable but acceptable quality. The problem why I am interested before we do some VCOs or others is that in a normal analog design, noise has something directly related to power dissipation, it is related to bandwidth, and it is also related to linearity. Okay. And then they also are connected to each other as well. Okay. They are also connected to each other. You have seen hexagons. So the problem is noise cannot be eliminated in design because they may affect any of the basic parameter design which you want to do. So apply itself you should have an idea how much noise I have and how much I can tolerate. Okay. That is the game in this. So please remember noise is something unwanted and therefore and also random. So what is essentially random? Some processes are called stochastic, statistical behaviors. So we do not know noise is how it behaves. Let us take a xt function which is periodic, and then we can deterministically say that if this is your function at any given time t1, t2, t3, I can find the value of x which is xt1 or xt2 or xt3 if this is periodic well behaved function. Okay. However, if the signal is random in nature as shown here, I cannot predictively say, because I do not know the nature of the function, that at any instant of time what is the value of xt I have. Okay. So that is my major worry, that it is indeterministic. There are also other issues in noise, and this is why I put it called correlated noise. Many of you probably are aware, I forgot the name, but in a stadium when people come, they are in 40,000 to lakh people, but that noise in the background hardly it is heard by you. Okay. But what is that wave that they call it when all of them stand? Maximum. If that is so happens, it makes a huge noise. So if the noise is correlated, it can have a bombastic effects. Okay. Uncorrelated noise normally distributes out, and an average value is not that strong. Okay. So please remember that noise have many features to understand, but we are only concentrating more from analog design side, though issues of other noise are also equally important. Of course basic idea of noise will remain same irrespective whether I do in analog, digital, signal processing or whatever area, noise is a noise, okay, so do not get too much worried. Is that okay, Siddhant? It is, even though the noise is random, most noise performs, if you see, they at least show some average value, it is not 0, some average value, okay. But of course that decides if you do it averaging for a long period of time, very short period it may become 0 or it may be very large or very small. So if you actually average it for a very large time, then the noise will have an average power. So for example, I have a resistor and I connect a VT source, then the power delivered is V square T by RL. So if I use the average power for any random source Vt, then it is 1 upon T tends to infinity, large, infinity does not mean really infinity, we use infinity because many of the integrals can be easily solved if I put infinity, okay. So minus T by 2 to plus T by 2, which is a period in which I am going to monitor, V square by T by RL dt is the average power delivered for a resistor, okay, by noise of Vt, okay. Please remember this T has to be large to get reasonable averaging, okay. So for example, if this is your function and you take a square of that, this will be something like this, and you can see there is some average value I can get, is that correct? As soon as I square it, I get some values which is reasonable enough, and then I can get some average value which is V square averaging, okay. In normal all analysis RL is chosen 1 ohm, okay. So voltage square is defined as watts, looks to be, but we say V square, okay. So it should have been in watts, power is in watts, but since R is always chosen 1 ohm per se, then the power average of a noise is essentially expressed in V square, that is voltage square, okay. That is the method of expressing. If there is additional load, you may multiply it to get the actual noise value, is that correct? This is a RMS value, if you take every under root of this, then this is called voltage per load if you wish, or just voltage. But in normal case this is time domain analysis. But if you look at that, if you take the frequency spectra for this, we find out that at different frequencies the power is not same, okay. This is called probability distribution with it, or also called PST, power spectral density, PST, okay. So if we actually, if you look at the average power, we should look for spectral density for noise, because at different frequencies noise have different values, okay. So that is the definition of noise spectrum. If noise average power is defined in frequency domain, we get what we call as noise spectrum, which is called power spectral density or PSD, okay, and it is defined as SXF, F is for frequency. Average power is carried by XT in a, let us say I have a noise which I pass through a band pass filter whose bandwidth is 1 hertz, okay, band pass filter of 1 hertz bandwidth. If I pass through and square it, okay, I get XF1T square, and in what is the range of frequency I use? Only 1 hertz. XF can be expressed in terms of volt square, okay, per hertz, volt square per hertz, and voltage is expressed in under root of average, so we say it is volt per root hertz. So noise is expressed as volt per root hertz, is that okay? At different frequency I actually calculate, like I calculated F1, please remember this 1 hertz which I made a mistake. The center frequency is F1 around which the bandwidth is 1 hertz, in a band pass you have to say where, okay. So I calculate similar thing at different frequencies F2, F3, Fn, okay, and then plot is PSD versus frequency at different frequency. Each will have a different value of this, so, and then I plot, essentially that is called the spectra. Is that clear? Please note down this, then I will show the figure. So what is my next stage? At different frequencies I evaluate xf2 square, xf3 square. Every time I have a band pass of 1 Hz around the frequency of my choice. Okay, so if I do this SXF at different frequencies, okay, average value of that, so I get a spectra. This is called noise spectrum or power spectral density SXF with F is something of course this is random, this is not that for everyone same curve will come. This is some random figure which I draw, this is the kind of spectrum we get for noise actually. And since SXF has a unit of x square, under root of that has a unit of volt square, by under root is volt, per hertz is per root hertz, so noise is essentially expressed as volt per root hertz. Assumption is RLs are unit loads, okay. नहीं तो वो भी एक term आती, but normally it is not used. There is a very famous noise, what is it called? White noise. So let us see what is the spectral density for that or spectrum for that. This is taken from Razai's book, any other figure is good enough, okay. So all that we did is find XF 3, 4, 5, 6, n with 1 Hz bandwidth for every point and then plot, okay. Is that okay? A white noise has a spectral density which says that from minus infinity to plus infinity is constant. That is why it is called white noise, okay. Of course, in a normal spectrum that minus infinity and plus infinity will have some larger bounds. So f1 to f2 is constant, okay. Though in definition it is minus infinity to plus infinite frequencies, the noise is constant, spectral value is constant. Now there is an interesting part that I can modify the content of white noise if I pass through a transfer function Hs, okay, which is Hf is Hs 2 pi jf. So if I have white noise, I pass through a transfer function of this nature which is Hf square. So if I multiply this, essentially I mean I am going to get a band limited SYF. That means this noise will get limited in the range of transfer function. So choice of transfer function allows me to get spectral density of my choice. You use this function as you want and white noise will convert into a pattern of your choice. Is that clear? That is the fun part in designing these circuits. Okay. Also normally this noise spectra is minus frequency to minus to plus, it is always shown, spectra is somewhere here because transfer function may be a square है ना, it can take minus value and plus value, square तो same में हो जाएगा. तो उसके भी एक मेथड है कि if between these two band of this, if it is SNX, okay, you want to see the last one, please have it, okay. One sided से two sided से one side जाते हैं वहाँ क्या बोलते हैं, integral of minus infinity to plus infinity twice 0 to infinity, same techniques is used, so just double the amplitude, okay. That is how noise spectra are shown one sided. After all we are doing averaging, averaging means integral, okay. So a two sided spectrum can be converted to single sided with double the amplitude. So this is the statistical behavior of noise. So this was the first concept we wanted to give you, that what is essentially noise is all about and how it is you can actually get the pattern of your choice. Okay. Which device or which system which is called a mixed signal circuit, which is one of the most popular, I don't know whether it should be called analog or digital, which actually requires noise shaping. What is it called? AD, ADC, DAC. A to D converters and D to A converters requires noise shaping to the maximum, okay. You may have 1 loop, 2 loop just to shape the noise. So that signal to noise ratio is very large. There is another term which is called signal to noise distortion ratio or SNDR, some mixed signal course some other time. So noise in analog is very important parameter, because if the, please remember what will happen if noise is larger, you will require larger power to actually dissipate, okay. So your first hit will be power dissipation, okay. Okay, is it okay? Figure trivial. Okay, so now let us see the 3 terms many of us use very unknowingly that they are as if they are same. There are 3 famous words which you use in the case of systems. One is called the device or circuit related noise, second term is distortion, and the third is interference, okay. All are bad but they are different, okay. So let us look the 3 differently, because we are more interested in the first part, but in systems you will require even the other 2 as well, okay. If the output waveform is, which is a function of input times some transfer function, and if that value which you now see in reality is not same as if it should have come, then you say output is distorted from the ideal value you thought you should have, okay. Like you have VO Vin characteristics, from these 2 inputs dV0 by dVin is constant, okay. So to say any value here or here, I can predict the output by just multiply is equal to mx, okay, C0 here. So I know the slope, that is the gain in this case, so I know dV0 by dVin. However, if I exceeds Vin1 or Vin1 either side, then the VO VI characteristics does not seem to remain linear. This essentially means you are entering a zone which is called non-linearity zone, okay. And as soon as you enter non-linearity zone, you can see dV0 by dVn is a function of Vn, okay. So it is a non-linear term, so if you expand it by Taylor series, you will get x cube ax bx square cx, higher order terms, okay, which means some power in the output is now related to 1 frequency, 2nd frequency, 3rd, 4th, and highest power delivered generally is into the 3rd harmonic, and therefore it is called 3rd harmonic distortions, okay. 2nd harmonic, in many circuits we tune it, that is we reflect it back, but 3rd cannot be, therefore the distortions are normally strongly related to 3rd harmonics, okay. We also feel as if it is due to only active device. No, non-linearity comes because of variety of other reasons. One of course is active device non-linearity, it is not linear, okay. So this non-linear distortion is essentially because of the non-linearity in the transfer characteristics, okay. So we say the distortion occurs due to non-linearity in the transfer function of active devices, but there is a possibility which is not just there, it is always there. Even in passive components there is a non-linearity. For example, cables, cable sabke ghar mein, it is like a transmission line, okay, it is an RLC circuit, okay, which also have different response at different distances, okay, because the Z0 change there, or Z reflected will be different. So even in a cable you may get a distortion, okay. So you always say do not increase length so much, put repeater somewhere. Even in fibers it are distortions, okay. There is also inhomogeneities in the path, the cable RLC may be varying all through, which may not be a constant, or in a fiber the multimode fiber becomes some way only few, not multi but smaller numbers. So much of the area is lost and therefore much is radiates. Okay. So any inhomogeneity in the path also may lead to distortions. So but we are more interested in devices because that is what we use often, but in systems anywhere noise can, distortion can occur. The next worry for me is the interference. So if you have one spectra, that is one signal spectrum, and you have another signal spectrum which is close by, then they may overlap. Okay. This essentially is called intermodulation. Simplest intermodulation thing can be understood without even a receiver. You have two transmission lines or two signal lines. If they are close by, due to just mutual inductance coupling, signal in one may connect to the signal in the other. This is called crosstalk. Okay. This is called crosstalk. When is crosstalk highest? Two lines are moving. When the signals are in opposite direction, the crosstalk is peak of both, okay, like differential. Okay. So highest crosstalks. Okay. So, but in RF receivers, because of the antenna input you receive, there is an image which actually interferes and creates higher harmonics. Okay. And that needs to be further filtered. Okay. All filters leak DCs. So that is major worry there some other time. Okay. So the interference is a very common in most RF circuits or RF systems. Okay. Like an antenna, you have two lines on any dielectric. As you bring closer, the radiation pattern of one will interfere with radiation pattern of the other. So intermodulation will start, and the pattern which you will see at the end at the antenna may not be single lobes, may be a multiple lobe with deflectivity almost lost. Okay. It may go scattered out. Okay. So everywhere the intermodulation is very common thing. We are not so much right now worried about these two, though distortions we will probably, but we will always say will remain in linear. So that's the reason why we call analog circuit as linear circuit, because we want to remain in linear modes. Okay, otherwise it could have been non-linear circuits. Okay. Okay, so here is the third and the most important among them is the noise, device noise. Okay. Electronic components produce combination of some noise with the spectra shown here. If it is constant, then we say it is a white noise. Then there are some noise which are inversely proportional to frequencies. They are called 1 upon f noise, and there are certain noise which are inversely proportional to 1 upon f square. This rarely you see in the books, so I added this for you. Okay. It is called popcorn noise. The word popcorn was used, of course, is another name if you are in a communication area, is called burst noise. Okay. Since the burst occur when the data rate is much higher than what the line can hold, then the noise starts picking up. So it is called burst. Okay. And the burst is essentially like popcorns, they pop up. So it is called burst. Okay. So it is called burst noise or popcorn noise. Yes, larger the frequency, smaller is the noise. Okay. No, but some other noise must be taking over there. Okay. So this is one kind of noise which has a frequency dependent noise. Okay. No, it is limited by lower frequency, that is what 1 upon f square is telling. Okay. However, there are another class of noise which are generally thermal noise as the word goes. However, other than thermal noise also there are other kinds of noises available, and these are named as short noise. Okay. Short. आपको एक नाम बताते हैं मिस्टर जॉनसन, ये सब नॉइज उन्होंने बनाए हैं. Okay. But the most commonly known thermal noise is essentially named Johnson noise. The first research was done by Johnson on every noise which I talk is essentially Johnson's papers. Okay. And these are almost 100-year-old papers. Okay. still stands. They do research 100 years अभी तक हम नहीं भूल पाए ना, that's research. न्यूटन के पहले भी एप्पल गिरते ही थे पर न्यूटन को दिखा, तो वैसे ही है. There are 100 things which we think are there but never bother. Maybe you are still time to do that. अभी थोड़ा रिसर्च का प्रॉब्लम क्या होता है कि इट इज मोर मनी डिपेंडेंट. You need large equipments. The third type of noise which is popular is called GR noise, and the last and the foremost which is very very troublesome in actual analog design is called KT by C noise. Okay, this is very very tough to handle. Okay, so you can see from here KT by C, I will come back to it, KT by C noise is generated from the resistor, but there is no R here. So that is the fun, that I have a resistor which is creating noise, but my noise is essentially independent of that resistor. Okay. So क्या हो रहा है फिर भी noise क्यों आ रहा है? So there is some issue which we will see in KT by C noise which is very very troublesome in analog design. You can see from here before I quit, if I increase C, KT by C will go down assuming T is constant. C बढ़ाओगे तो सभी एनालॉग चेंज हो गए, तो C को तो हाथ नहीं लगा सकते ज़्यादा. तो दैट इज द वरी, C इज कैपेसिटर, सो C को होल्ड करेंगे तो एवरीथिंग गोज अवे. नाउ दैट इज द प्रॉब्लम विल सी विच C is an output capacitance. Okay. Now any time you leave C, you have a problem. Okay, and we'll see now. So this evening we'll start with the definitions of each of them and go up to device and to a circuit how to calculate noises.